Hello class and welcome back. We are in week 4 according to my uh, calendar, and week 4 we begin chapter 4 from our textbook, and this chapter will take 2 weeks, weeks 4 and 5. So I will do part A of this chapter today with 2 recordings, one for the theory and one for the problems, and then the remaining material of this chapter part B will be next week. Okay, so with that plan, let me move ahead to the next slide, slide 2, where you can see the topics under chapter 4. So there's really 11, but the last one I think I'm going to ignore it. So we'll probably do the first 1 to 10, and in part A, this recording, I will go up to 4-5, electric scalar potential, and the remaining stuff we'll do in part B. Okay? All right. So moving on, I am on slide 3, and I will expand it. Sorry, so you can see better. And this slide, in our textbook, we get an overview or an introduction of what's called Maxwell's equations. Now, Maxwell's equations pretty much covers everything in electromagnetics, right? If somebody asks you what's electromagnetics, you can say Maxwell's equations. Maxwell's equations, there's 4 of them, 1, 2, 3, 4, as shown here. They pertain, or they are about the behavior of electric fields and magnetic fields, and sometimes the two are related, interconnected, right? So when you are able to study them separately, the electric and the magnetic field, with no connection between them, such a situation is possible only when certain conditions are met. Particularly the fact that dou by dou t, right? Any of these vectors, Ed or Hb, if they are not changing with respect to time, then, or other ways they are static, they are not moving or they are not changing, then we call them static, and then we have 2 fields of study, electrostatics and magnetostatics. Also, Maxwell's equations get modified. In particular, this second curl equation becomes 0, and this third equation, the gradient equation, also becomes 0. So under static conditions, these are the Maxwell's equations, and we'll look more deeply into this. This slide is just a general introduction, so don't get too worried if you don't quite understand these yet. But the quantities that we discuss in this chapter and also the next chapter, magnetostatics, are primarily these, and you have already seen them. They were introduced to us when in chapter 1. E is the electric field intensity, D is the flux density, and they are related like this. Similarly, H is the magnetic field intensity, B is the flux density, the magnetic flux density, and they are connected like this, right? So that was just an overview of Maxwell's equations, and in the rest of these chapters we will do deep study of each one of those. Okay, so next topic is charge and current distributions. So there's a section called charge density, or actually this should be distribution, I'm sorry. And similarly the other one, and I will change that before I post this document. But so what is charge density? So here are some definitions, and here are some pictures, and again this is not from our textbook. So we know what a point charge is. It's a single charge, and a point charge generally means a small charge, small, small meaning size wise it's a very small item compared to the surfaces and the volumes that we talk about. So such a charge is called a point charge. Generally we use a small q or a big Q, doesn't matter. And then we now start to define some new things, such as, for example, a line charge. A line charge is the charge. Now charge is always in coulombs, right? So if along a line, right, just think of a string, right, or a wire, and we say that there is charge all along the wire, the density of that charge, that means how many coulombs per meter, right, is the density, and that's shown as rho. This letter is a rho, Greek letter, with a suffix L. So for a line charge we say rho L. For a surface charge we say rho S, and that is the charge on the surface, the density of that charge. Similarly, volume is with a V, rho V. So rho L, rho S, rho V, and we're going to use these a lot, so try to become familiar with them. The real definition of this is rho V is limit delta V tends to 0 as delta Q by delta V, which we also write as the differential dQ by dV. So we have dQ by dV, dQ by ds, and dQ by dl as the real definitions of these charge densities. Now once you know the charge density, you can do the opposite, right? So this is a derivative. If you do the integral, you get the total charge, right? So if you take the integral of the charge density over the complete volume, right, the limits you apply have to cover the volume. If you do that, then you get the total charge inside that surface, or similarly the total charge on the in the volume here, surface here, and length here. Okay, all right, I'm going to move on after having introduced charge density. So we have some examples here that we will come back to later. These are from our textbook, example 4142. So we have a small tube that's given, cylindrical tube along the z-axis, and a certain charge density is given, rho L, and then we have to find the total charge in that tube. Similarly for a circular disc. So we'll do that later. Hold off for that. Here's a problem, also we'll wait. Alright, so now let's talk about current density. So there are two types of currents. You may be surprised, right? Maybe you've heard of this, maybe you haven't. Actually there's one more type, but let's stick with two. The one current that we know very well from electric circuit analysis is really conduction current, where we know in a copper wire, for example, we know that there are atoms and there's electrons in the outermost shell, or electrons in the outermost along the circumference, and so they jump from one atom to another, causing conduction current, right? So that is conduction current, and generally current J is the current density in amperes per square meter. So whether it's here or here, this J means amps per square meter of the surface, right, of the area. So that is conduction current, and generally conduction current is connected to the electric field that is causing the current by this formula, J equals sigma times E, where sigma is something called the conductivity of the conductor. Okay, and Ohm's law satisfies oh, there's something wrong here. This should be an integral. Sorry, I think I have to fix this. I think this is similar to this here. Anyway, that is conduction current. Now let's look at something new called convection current. So convection current is, it is possible even in a vacuum. So whether you have a conductor or not, it's possible to have electrons go through a volume or a surface, and that happens when the charged particles, all of them go from point A to point B. This happens, for example, in beam of electrons in a vacuum tube, right? You have a tube, there's no air or no atoms, nothing in it, it's vacuum, but you're still able to push electrons from one end to the other. Such kind of a current is called convection current, and so the density of that is related to the it's connected to your charge density rho v, and also related to the density, the speed at which the electrons are moving, right? So those two factors together give you the current density in amperes per square meter. So this rho v, as we saw from this previous slide, is the charge density, right? So the charge density times velocity gives you the current density. And then once you know the current density, which is amps per square meter, if you want to find the total current flowing across a surface, then you integrate over the area of the surface, J dot ds, and you get the total current. Okay. So remember these two formulas are important. We don't do much with this, I think, but we do have problems on this. In fact, here's a problem. We'll come back to it later. But you're given a small cylinder, which is an cylindrical shaped electron beam, and we are given the charge density, and we are asked to find the total charge and the magnitude and direction of the current across this. So anyway, we'll wait to do that. We're moving on to a very important topic, Coulomb's law. Coulomb's law and electric field. So there's three sections here, and we'll go one at a time. Okay. Now I assume everybody knows Coulomb's law, right? This is high school physics. We have learned a little bit at least. Actually, hold on. Yeah, we all know that if there is a charge that is brought into an electric field, then the force experienced by that in newtons is given by, the product of that charge times E, the electric field in density or intensity. And what is E? It's the source charge Q, which creates the field, divided by 4 pi epsilon r square. So we have seen this before, and we have just introduced that again, and I have repeated everything about epsilon that I had already shown you before. Epsilon 0 is in air, epsilon in any other media is written as epsilon equals epsilon r into epsilon 0, and epsilon r is something called relative permittivity or dielectric constant, and you use that in problems. Okay. Now remember epsilon 0, this value, because we'll use it quite a bit, 8.85 times 10 to the power minus 12. So basically Coulomb's law is telling you what force is experienced by a charge in an electric field. Okay. All right. So before you can calculate force, obviously you need to find the strength of the electric field. And so if you have multiple charges, let's say you have Q1 and Q2, two charges, what electric field do they create at a point, let's say P, right? So how to solve that, how to calculate that using vector methods. is what this slide is about. Now you can see this is vector addition, E equals E1 plus E2, where each of these is a vectors, but E1 is written like this, E2 is, I mean, when you finally solve, and this is in the textbook, so I haven't gone through every step, but when you solve it at point P, the resultant, because of the two charges Q1 and Q2, each one is giving out one electric field. Q1 gives you E1, Q2 gives you E2, and the sum of it depends on the location, obviously, right? That's why we are using vector analysis, and so this is how you write it. Okay, so you can generalize it as 1 by 4 pi epsilon, and then n runs from 1 to n depending on the number of charges. On the top you have r minus r1 ri, right? So that's r minus r1, r minus r2, r minus r3 multiplied by the corresponding charge q1, q2, q3, and in the denominator you have a third power and r minus the same thing on the top, but here you have the magnitude of that vector, right? R minus r1, in the denominator you take the magnitude, but you have to raise it to the third power. So this is derived in the textbook, but obviously you need to learn this or remember this at least so that we can use it in problems, right? On the next slide, slide 13, there is a problem. It's an example actually, just to show if you have two charges, how do you find the net field, the electric field strength E at a third point based on these two charges. Also, part B says find the force on another charge of 8 into 10 to the power minus 5 coulombs. So all this we'll wait to look at it in my next recording. Let's move on to something called continuous charge distributions. So far we studied point charges, right? A small charge and how it creates, how charges and how they create a resulting electric field at any point. Now what if you have a charge distribution? That means you have either a line or a surface or a volume, and charge is distributed uniformly all over this volume or surface or line. Then what is the electric field at any given point P, which is at a distance r prime from the surface or volume, etc. So here are the three formulas. Again, this is simply applying Coulomb's law, so I'm not going to, you apply Coulomb's law for a small differential area, right, or volume, and then you integrate. So we have seen that technique in the past, so I'm not going to repeat it. It's in the textbook. If you're interested, it'll be helpful for you to read through it and understand how the derivations have been done. If not, at least remember that the formulas are available for line, for surface, and for volume, and we need to practice using these formulas so that we understand the logic. Now, of course, these are vectors, so E is a vector in every case, so it has at least one direction, and that is R. Generally, R is along the same R and headed out normally from that surface or volume, right? Normal means going out perpendicularly. So that is one direction along which the field is shown. It may be multiple directions, but at least you'll have one direction. Okay. All right. So, well, R actually is a unit vector along the direction, right? So it definitely can have one or more dimensions. If it is Cartesian, it may have all three or just one. If it is, cylindrical or spherical, also there may be multiple coordinates within R. R is the unit vector. Remember that. All right. So here's another simpler formula from a different textbook where clearly you can see the formulas don't seem so scary. They are still integrations, but here you integrate dl, here you integrate ds, here you integrate over dv, everything else is a constant, and ar is a unit vector and r represents distance. Okay, all right. So here's an example 4, 4 and 4, 5. Now even though these are shown as examples, I would call them more derivation of formulas, right? And you'll see the same configuration. So here we are talking about a ring of charge, right? An example 4, 4. And this is on page 185, by the way. And I do request you to take a look at it because even though this is an example, like I said, you have to understand how a formula is derived, right? What logic does he use to determine the field at a given point E? So here there's a ring of charge. A ring is a very thin ring. It's like, you know, what you may wear on your finger, much thinner than that. So if you're given a ring of charge, it's a linear thing, so it's only concerned with length, and it has a charge density of rho L. Given that, we are asked to find, now the ring itself has a diameter or radius of b. So given that, can you find at a different point along the center axis of the ring, can you find the field density? So that's the derivation, and it's basically taking Coulomb's law again, creating a small differential element of length, you know, dl, and then finding by Coulomb's law what is dE, the differential E on it, and then integrating it over the entire length. So if you do that, you come up with this formula, E equals z times, z is the direction, it's in the z direction because we are only been asked to calculate along the z axis, and of course the original q also appears. So there's a couple of ways that this formula is written. I only showed you one in terms of total charge q, but you can also write that formula just in terms of rho L also, right? So this is one form, but you'll see the other two forms also. So please take a look at that. Similarly, take a look at example 4-5, where he talks about a circular disc, not just a ring, but a whole disc. That disc is charged, it has a certain surface charge density, and again, how do you find the intensity of the field at a given point perpendicular to the surface of the disc? So that's another derivation also in example 4.5. So take a look, see how the methods, what method is being used to derive all these. Once you know the method, then you're okay. You need to remember these formulas, maybe write them down on your cheat sheet. And if the formula is really complicated, I may just give it to you when we are doing a test or something. But you need to know what each of these numbers are and quantities are, you know, B here, H here, and so on. So please pay some attention to these two examples and learn them. Similarly, going from a circular disc to an infinite sheet of charge. So assuming that there is a huge sheet of some material which is all charged, how do you find the charge density at a given point? So from here you can easily come to here, okay, from this formula to this formula. So all that is an example 4-4 and 4-5. All right, I'm going to move on. Now this example or this derivation is slightly different we do have a line charge, right, that we have seen somewhere else. We saw the ring of charge. It's a similar approach. And hold on. Yeah, here is, where did we see a line? Yeah, here we have a line charge, and the same idea of a line charge on that was on slide 6 is now appearing again. Hold on, I'm on slide 17. So now the line charge is not starting at the origin, it's slightly higher than that, but this I found in another textbook, and I'm just giving you the final formula because we have a problem that is related to this formula. So I thought, I found this, I might as well share it with you. So here is a line of length AB, whatever is the distance along the z-axis. And how do you find the charge density E at any point xyz on the Cartesian coordinates? So that the general form, and if this is an infinite line, then the formula becomes this, okay? And these angles alpha 1, alpha 2 are these angles, the angle that this vector from point A makes with the point that we are interested in, which is at r distance from the z-axis, okay? So try to understand alpha 1, alpha 2, because then we have a problem that uses this later on, okay? So you'll always notice any formula for E, it involves the charge density, right, on the top, and then you have this 4 pi or 2 pi, and then the epsilon always appears, and then r, which is generally the distance or radius if it is a round thing, and that also appears, okay, followed by some vectors, unit vectors in one or more of the coordinates, okay. All right, so I'm going to move on to slide 18, which is also a problem. This is along an arc located in the x-pi plane, so we'll do this later on. Okay, moving on to section 4 of this chapter. So we are on topic 4-4, and we come to another important law, Gauss's law. Again, maybe you have studied this in high school physics, maybe not, but we are revisiting it. I know that when I studied some of this kind of stuff in high school, the law is the same, but it would not appear to be so complicated. It would be more arithmetic rather than calculus. So we kind of ignored the dimensional aspects of it when we studied this in high school. We ignored the fact that there is always a direction, but we just worked with the magnitudes. That's why it was all algebra. Now we talk about three-dimensional space and coordinates. That's why these same formulas now seem a lot more complicated. Well, it's not too complicated once you understand the theory and how to apply calculus. All right, so with all that introduction, let's see what Gauss's law says. Now, before we go to Gauss's law, which is actually on my next slide 20, in slide 19, I've introduced a few more things for you to refresh your memory. All right, so the vector field D, right? We know vector field can be either in terms of E, the field intensity, or the flux density D. We have been introduced to both of these in chapter 1, and I have just refreshing your memory that D, electric flux density, is related to electric field intensity through the epsilon, where epsilon is the electrical permittivity. Okay. Now, electric flux. So if D is a density, then to get electric flux, you have to integrate, because density just generally means something over square meters or cubic meters or something like that, right? Density means how much per unit area or per unit volume. To get the complete quantity, you then have to integrate over that surface or volume, right? So here we are talking about surfaces generally. Gauss's law only deals with surfaces. So the electric flux phi is integral of d, which is the electric flux density, times a suitably found differential surface area, okay, ds. So this formula is important. Flux equals integral d dot ds. All the formulas derived for E, right? We did a lot of E's previously when we looked at Coulomb's law. They can all be written in terms of d because the difference between d and E is only a constant, right? Epsilon. So that's what this says, that you can work with flux either in E or in d. Lastly, a reminder that the divergence theorem, remember we studied the divergence theorem in terms of the field intensity E, that also can be written in terms of electric flux density d. So instead of E dot ds equals del dot E, now we just write it as d dot ds over the surface equals del dot d dv over the volume. Okay, so I'm bringing all this together because you will see all this in the next slide when we talk about actual Gauss's law. So again, you're imagining a field. There's a charge here. It's creating E, which is also creating D, right? Because it's the same thing. And then these lines are called flux. And then the unit vector is always in that direction, n, which is normal to this surface. Okay, all right. Now let's come to Gauss's law. So in its simplest form, you can say Gauss's law states that the total electric flux phi, is this phi? Yeah, I think so. Did I say it somewhere? Hold on. Yeah, I think it's phi. All right, let's psi. I think it's psi, psi. Okay. So total electric flux psi through any closed surface is equal to the total charge enclosed by that surface. So this charge Q in coulombs gives you the flux, and the flux equals Q. So not a very great discovery, I think, but it's so important for electromagnetics. All right. So now let's start opening this a little bit, or peeling the onion as they call it, and see what else we can find. So psi, which is Q, is also, you can write it from the previous expression here as integral dot d dot ds, right? So integral of the flux density gives you psi, and Q enclosed we know by applying the formula for flux charge density. So rho v is charge density. If you integrate that over the volume, you get the total Q enclosed. So basically, because this and this are the same, the left sides are the same, the right sides become equal. So now we can say that the integral of the flux density over the surface equals the integral of the charge density over the volume. So integral of flux density equals integral of charge density. Okay. Also, according to the divergence theorem, this integral can be written in terms of the gradient, right, as del dot d. So comparing the two equations, we can say that this del dot d equals this rho v. So what we have come up with is the fact that the volume density is nothing but the gradient of the flux density. Okay, so Gauss's law in differential form, also called the first Maxwell's equation, implies that the volume charge density rho v is the same as the divergence of the electric flux density, hence written as del dot D. This is the flux density. Okay, so this is one form of Gauss's law. So here are the two forms of Gauss's law. Okay, first form says it gives you a del dot D, it gives you equals flux density, charge density. The second form, which also comes from here, right, because this equals psi equals q, right, q enclosed. So this form gives you the fact that when you take the flux density and integrate it over the surface area, the surface enclosing the charge, then the integral equals the charge. Okay, so I put an arrow here because what I notice is for a lot of problems we use this form rather than this. We may do this later, but for now remember how to this has more importance. Okay, so here's a nice graphic from our textbook. It shows you that there is Q and that there is a surface or a volume. Actually this is a Gaussian surface enclosing the volume. So remember the difference, right? There's both S and V that we are talking about. So there is a volume and then there's a around that volume, or let me put it this way. Let's say there is a huge soccer ball, right? It's a very big one. It has a lot of volume, but within that volume, and there may be charge all over, but within that volume, if you zoom in on a small surface, Gauss's law applies to that small surface within the soccer ball. It may apply to the whole soccer ball also. It may apply to the whole earth. But generally, we take a small portion and we draw a surface around it called the Gaussian surface, shown by S, and then we can apply Gauss's law to it. So, the integral form of Gauss's law states that the outward flux of D, this is D going out, through a surface is proportional to the enclosed charge Q. So if you have Q outside here, and actually I saw an example somewhere that maybe I should have brought here, but let's say there is some charge outside, then that charge, because it's not within this Gaussian surface, you should not use it when you are doing the integral. So the integral only applies to the charge within the Gaussian surface. That's important to understand. Okay. All right. Gauss's law provides an easy method of finding E or D for symmetrical charge distributions such as a point charge, an infinite line charge, an infinite cylindrical surface charge, a spherical distribution of charge. So depending on all these distributions, depending on which one you are working with, Gauss's law, particularly this, can help you find E or D. Okay, isn't that wonderful? All right. So, for example, point charge. So we have one charge here and we have a sphere or a Gaussian surface, which is a surface. Sorry, I shouldn't call it a sphere. So how do you find E or D or E, actually both, at a certain point, which is R from the Q? Okay. So to do that, I show you this, and I don't have too much time, so I'm going to skip some of this. You can read this. This is in our textbook. I just gave you a quick summary of what is there. So what do we do here? We need to basically do D, right? We need to find D at a certain point. D is a vector, so it has a unit vector to give you the direction, and then it has a magnitude, dr. So we need to find dr. Now Q equals, right, the charge enclosed is this integral. So q is the d integral times ds. So s is expanded in this way. So it basically becomes a scalar integral, right? Because r and r, when you product them, dot product, the vectors go away. So you have dr ds. Now dr is a volume integral, right? I mean, this integral is a volume integral. So that's what I show you, 3 lines of integration, and that gives you 4 pi r square. So to see this, see example 3-5, and the only difference from example 3-5 where we did a sphere is that theta goes from 0 to pi. It's semicircle. So go ahead, take a look at that, and you will come up with a value for dr, like from this, q equals this. So dr becomes q by this, and to complete the vector you put the unit vector back r, and then once you know d, e is just dividing by epsilon, so you get e. So that's how you get d and e for a point charge, for an infinite line charge, for an infinite sheet of charge, for a uniformly charged sphere. So these formulas are in, and these derivations are in the textbooks. I'm not going to show you all the derivations, but I would advise you to at least spend a little time looking at each one so that you understand the methodology, because that helps you even when you're actually solving problems using these formulas, right? All right. So here's a formula to apply Gauss's law. Here's a problem, so we'll wait to do this later. And we come to the very last topic called electric scalar potential. So let me quickly try and wrap this theory up so that next recording we can do problems. So all of us know scalar potential, I mean electric potential, a little bit from our circuits business, but here is more of a electromagnetics approach to understanding potential. Okay. So we have seen that electric field intensity can be obtained from Coulomb's law, from Gauss's law. Another way of obtaining E is from the electric scalar potential V, to be defined in this section. The term voltage is often used. It's just short for voltage potential, and it's really the same as the electric scalar potential V that we are going to talk about here. Okay, so here is a definition of voltage in terms of energy or work. Okay, so differential electric potential is what we always start by defining a differential, right? You take a small movement. So if a charge is in a field and is being moved between 2 points, we know you have to put some force on it, or it experiences force. So when you have force, you have work being done, right? So that work is stored as energy, right? Potential energy. So dV, electric potential, is the ratio of the work done, differential, by the charge being moved, and this is actually related to E as this formula. So this is in our textbook. Take a look and read it and try to understand what he's saying. But more important than this is this for our purposes. So if you take this dV and you integrate it between 2 points P1 and P2, then you come up with a formula for the potential difference for moving a charge from point 1 to point 2 along any path, and that is this integral. E dot dl, the intensity along a certain vector, a linear vector, the integral from point 1 to point 2 gives you the voltage difference or the potential difference. And it's also important to understand this, that is equal to the work done divided by the actual value of the charge q. This should be small q, but sometimes we use big Q. Okay, so this formula is important, and this is often written as this. So V21 that is the potential difference between 2 points 1 and 2, is V2 minus V1, which is the integral of this. Now generally we assume V1 equals 0 because we say point 1 is at infinity and we define the potential at infinity to be 0. Then this integral just becomes this integral. Okay? So the potential at any point is the potential difference at that point and another chosen point, which is generally infinity, where we assume the potential is 0. Okay? Alright, let me quickly finish this. I know we are running over time, but here's another way of writing the same or describing the same situation. So we have, this is from another textbook, we have a path, so A and B, so maybe a charge is moving from A to B and it's along a curved surface and it exists in a field E. So all these are vectors RA, RB, and at any point you can say a small distance dl is being moved, and so what is the voltage there, right? So you can then for the total voltage across from A to B, you apply the integration, right, of E dot dl, and that voltage between A and B, VBA, is shown as minus integral VB to A of the field intensity multiplied by the dl, so E dot dl. So you can see that is another way to derive VB minus VA. One thing I want you to be cautious of is how is dl derived. dl is, as shown here, it has a unit vector and a magnitude called dr, which is along this direction, right? It's a small r there, and the product of that, r times dr, gives you dl, and we use this in some problems later, so make sure you understand why that is. Okay, you may have to read my chapter 3 notes. All right, so now we have, if you have multiple points q1 and q2, then what is the resulting electric potential due to these multiple points? And it's the same formula that we have seen before, but here we are talking voltage, not field intensity, E. So the formula has the same form, and I have a little problem here, an example. So please take a look and make sure you understand how we calculate the voltage at any given point if there are multiple charges in the neighborhood and each one of them has a vector from the origin to a certain point. Okay. All right. So if you have continuous distribution of charges, then also you can find the voltage. So that voltage now uses the distribution formulas, and they are shown for line, surface, and volume. Okay. This is also from our textbook. Take a look. You know what? Maybe actually we're almost done. So give me a minute and we'll finish. So the line integral around any closed path equals 0 because it's a conservative field. Okay. So because of electrostatic field E, not electrodynamic, right? Electrostatic field always gives you 0 on this product. And so Stokes' theorem says that this equals this, right? So we write Maxwell's second equation as the curl of E to be 0 for electrostatics. Okay. Also, this formula E equals minus gradient of V, where V is the voltage potential at a certain point. So this is another important formula. It just connects field intensity to potential using the del function. Okay, so this is another formula to remember. Here's an example. Take a look at this. And then we have a problem on electric potential, actually a bunch of problems that we'll look at later on. Okay, Poisson's equation is the final slide. just take a look at these equations. We are not doing much with them yet. Maybe we'll do more with them later on. Okay, so with that I will stop.